Hello. Let's continue and actually finish our talk about orthonormal systems in Hilbert space. And we have to formulate and prove two more theorems regarding orthonormal basis. First theorem is criterion of basis. Let us have Hilbert space and orthonormal system. Then the necessary and sufficient condition of this system to be basis is density of linear envelope on this system in H. So this is orthonormal basis if and only if linear envelope of our system is everywhere dense in H. I remind what linear envelope is a set of elements what can be represented in such form. X from H. There is an element such what there is a number and some combination of constants such what x can be represented as a linear combination of vectors or some finite numbers of vectors from this system, and this is linear envelope. So let's prove it. No. Actually, it's not very hard. So we have basis. And if we take some arbitrary element from H, this element is a sum of its Fourier series. What means what distance between x and finite sum of this series converge to 0 if n goes to infinity. But here we have an element of linear envelope. So we can approximate x by elements from this linear envelope. What exactly means this? Because x is arbitrary element of H. Um, let's prove the opposite. Let us have this. It means what for each x and for each epsilon we can find the number n and constants alpha 1 to alpha n such what x is can be approximated with accuracy epsilon with this linear combination. But if we consider here the part of Fourier series, here there is a best approximation to x in a linear envelope of first n elements of ek. So this distance is smaller than this one, so it means what Fourier series converge to x, and so x is sum of Fourier series and means what we have orthonormal basis. So this theorem is proved completely. Next theorem let's call it as well existence of orthonormal basis. If H is separable Hilbert space, then we can build an orthonormal basis there. So in each separable Hilbert space, we can build an orthonormal basis. Proof. H is separable. So we can find a countable everywhere dense set. So there is a countable set such that H belongs to, actually equal to closure of this set. It means what psi k is everywhere dense. Next we will perform several operations with this family and construct an orthonormal basis and prove what it is indeed orthonormal basis. Let's phi 1 is the first non-zero element of this system. So we don't know anything about this system except just one fact, what it's everywhere dense in H. So it can happen that first 100 elements of this system are equal to 0, but it cannot be that all elements of this system are equal to 0, because if all elements are zeros, we cannot approximate each element with element of this sequence. So there are non-zero elements. So phi 1 is the first non-zero element. So I will not write it formally, but just say. So phi 1 is the first non-zero element in this system. And if we already have chosen k elements, then phi k plus 1 is the first element of this sequence such what such system is linear independent. So if we have already have k elements, then our next element from this system is the first element from this sequence such what this family is linear independent. It can be proved what resulting sequence will be infinite, and it cannot be finite. So please think about it, and we will discuss how it can be proved. So this family cannot be finite, it is infinite. And so what did we do in this space, in this step? We dropped only linear dependent elements. So, and all linear independent vectors in this system remained here. It means what our initial systems belongs to linear envelope of this new system. So we drop only linear dependent vectors. That means what they can be represented as a linear combination of existing vectors. So this is why we have this. It's important. Next, we perform so-called Schmidt orthogonalization. So let's E1 is normalized phi 1. So phi 1 divided to its norm. As we remember, it's non-zero, and actually all elements of system phi are non-zero. So we have chosen first element, and let us already assume what we already have chosen k elements, and let's choose ek plus 1. So ek plus 1 dash is equal to phi k plus 1 minus sum from I1 to k, phi k plus 1 ei multiplied to I. So we subtract from phi k plus 1 some linear combinations of vectors ei. Let us study the properties of this new vector. If we multiply it to e, say j, for each j from 1 to k, we will get phi k plus 1 multiplied by ij minus I1 k phi k plus 1 And sorry, I forgot to mention what our first vectors are already orthonormal. So this system ei multiplied by ej gives Kronecker symbol. So 0 if I and j are non-equal, and 1 if they are equal. So here we have Kronecker symbol, and all terms here are equal to 0 except 1 when I is equal to j. So we have phi k plus 1 ej minus phi k plus 1 ej. So it is 0. So this element e dash k plus 1 is orthogonal to all previous vectors 1 k. And finally we obtain ek plus 1 as ek divided to its norm. So we have built the orthonormal system. So ek, this new system, is orthonormal system in H, and can be seen what phi k plus 1 can be represented as a linear combination of all vectors of first k plus 1 elements of system E. So it means what system phi belongs to linear envelope of new system EK. So if all vectors of this system can be represented as a linear combination of this system, what is written here, the same can be done for linear envelope. So any linear combination of vectors phi can be represented as a linear combination of vectors E. Each vector in this linear combination can be represented as a linear combination of these vectors, and then linear combination of linear combinations is a linear combination. So linear, let's write it here in this part. So linear combination of phi k belongs to linear combination of EK. But as we see here, this linear combination contains our initial everywhere dense set psi k. So linear envelope of EK contains everywhere dense set. So if some set contains everywhere dense set, it is itself everywhere dense. So closure of linear combination of EK is equal to H. Because once again it contains linear combination itself contains initial system psi k. And according to our previous theorem, it is enough for orthonormal system to be basis. Let's finish our proof, and also our chapter about Hilbert spaces is also finished. Of course, next semester we will see many examples of application of this Hilbert spaces theory, but it will be already applications of these Hilbert spaces. So thank you very much.